So far in calculus, we've seen a bunch of different named theorems. We have the intermediate value theorem, the extremum value theorem, the mean value theorem, but in this particular video we're going to talk about the fundamental theorem of calculus. And in fact, there's actually two parts. This one's going to be part one, and there's a second fundamental theorem of calculus. That's going to be in the next video. Now, if we're going to call it the fundamental theorem of calculus, it better be a pretty big idea. And indeed, this is. When we talk about the fundamental theorem of calculus, the large picture is that there is derivatives and there is integrals, two different important components within calculus. Indeed, if we talk about the derivative, we're talking about things like the slope of a tangent line at a point. Well, if we're talking about a definite integral, we're talking about like an area underneath of a curve. These are two very different geometric concepts. And what the fundamental theorem of calculus does is basically take these two different ideas and find a way to relate them, to kind of mash them together. This definite integral, the integral from a to b of f of t dt, this is going to represent geometrically the area under the curve, the area above this particular interval, a, b. Now, this is a static thing. This is a number. If you gave me an a and a b, you would compute this and it would be some value like 7. But what if instead of a to b, I make a slight change and I say that now it's the integral from a up to x. And indeed, I'm now going to call it something. I'm going to call it a function g of x, because indeed, this is a function of x. Think about it this way. For every value of x, you get a different number out. A is some fixed thing, like say 3, and then you could ask 3 up to any other value of x. To help visualize why this is such a dynamic thing, imagine I take this particular x that we have here, and what if I move it? For every value of x, you get a different curve, a different region you're considering, and you get a different answer out for what that area is. G is a function of x. One thing to note here is that in this particular curve, I've managed to draw one which is a positive function. This function of x is over the x-axis. So as I go to the right, as x is increasing, the area is also increasing. So this g of x here is an increasing function as long as f is positive. If in a different graph the function dipped beneath the x-axis and was negative at some point, then the g of x, the accumulation function, would start decreasing at the point as I was adding negative areas, contributions from beneath the x-axis. Now, one point I want to make clear is that in this accumulation function, there's an a, there's an x, and there's a t. But they have slightly different philosophical meanings. When I look at the a, for example, a is just some fixed number like the number 3. And I'm saying that all of these integrals, for every value of x, I'm going from, say, 3 out to wherever my x would be. So a is thought of as a constant, a fixed value. The x here, that is the variable in my function of x. G is a function of x, and for every value of x, you get a number. So then, what's the t? Well, the t is a bit of a dummy variable. This is the variable when you're actually doing this integration. If you think of breaking it up as a limit of sums via the definition, you'd have a t there. That's the thing you do to actually compute the area. And so for every value of x, you'll use the t's to be able to compute what that integral is going to be between a and between x. Now, what is the fundamental theorem of calculus concerning? I told you it mixed derivatives and integrals together. Well, what it's going to ask is this. Can I take the derivative of this g of x? G of x is a function. It depends on x. Derivatives takes functions to some other function. Why don't I try to compute the g prime of x? So let's ignore our picture for a moment and try to do that. Let's try to go and look at what the derivative of g of x is, and I will remind you that the definition of the derivative, when back in the day when we actually defined it, the definition of the derivative was the limit, as h goes to 0, of g of x plus h minus g of x all divided by h. That is my formal definition of the derivative. Okay, so let's do that. Well, g of x plus h and g of x, those are both defined in terms of these funky accumulation functions. So if I replace those, what I have instead is going to be the limit as a goes to x plus h. That's taking g and plugging x plus h in. A up to x plus h of my f of t dt. And then I subtract off g of x, so I subtract off the integral from a up to x of f of t dt. So this is what my limit does to this g function when the g is the accumulation function, the integral from a up to x of f of t dt. So now let's go back geometrically. Let's just look at the numerator of this difference of these two accumulation functions. Let's try to understand what that is. Because if I go here and write that, so this is the same numerator here, how can I visualize this? Currently, I've graphed the integral from a up to x, but let me overlay a to x plus h. It's going to look a little bit like this. That is, it's an integral from a all the way up to x plus h, and if I think of x plus h as slightly bigger than x when h is greater than 0. So now I want to do the difference between the two things. So the red is going up to the x plus h, the yellow is going up to x, and then their difference, so it's the big area minus the small one, their difference is just going to be this little red strip here. And I combine that. This little red strip is the integral from x up to x plus h of f of t dt. Now, this integral is the area under the curve, so can I approximate what this little red area actually is? I think so. Indeed, if you look at the width, going from x to x plus h, this width is indeed just h. Now, this little red strip is not quite a rectangle. Maybe on the bottom it looks like a rectangle, but it's some weird curve along the top. However, imagine that my h was really, really small, so my x and my x plus h were right beside each other. Well, you could approximate this as a rectangle with a fixed height. That is, we could say that this was the rectangle that had the width h, but had a height of about f of x. And you might say, well, hold on, no, it's not quite a rectangle. But as my h goes to 0, this is approximately a rectangle of width h and of height f of x. Let's take this result and let's put it back into my definition of the derivative, the definition for g prime of x. So this is where I was at earlier. I had my g prime, I did my definition of the derivative, I plugged in my accumulation functions, but now I can do something with that numerator. I know what that is. My approximation was that that numerator was just going to be the same thing as the integral from x up to x plus h of f of t dt, and that was approximately just going to be f of x times h. And then I'm just about done with my proof here because I got an h on the top, I got an h on the bottom, I can cancel those, and that just leaves me with f of x. So the grand statement of the fundamental theorem of calculus number 1 is that the derivative with respect to x, my g prime here, the derivative with respect to x of the accumulation function, the integral from a up to x of f of t dt is just f of x. And doesn't it sort of look here like derivatives and integrals cancel them? Indeed, we've got a derivative and an integral, and it does cancel. Now we have to be a little bit precise about what we mean by that. What we mean is exactly this statement. Note, by the way, that the t, that dummy variable that we have here, it becomes an f of x at the end. So this is a function of x, so the final answer should be f of x. It shouldn't be f of t, the dummy variable. And also note that this is very precisely needing to be written, the derivative not just of any integral, but precisely the derivative of the integral from a value up to x of some particular integrand in terms of t. So that is the fundamental theorem of calculus. It does have an assumption. It has that this original function f needs to be continuous on a up to b, where x is some value in between a and b. But there you have it. Finally, let's go and use this theorem for something. I've got an example. It's kind of a bit of a weird example, but we're going to apply it. So let us imagine that what my goal now is to be doing the derivative with respect to x of the integral from 7, not up to x, but 7 up to x cubed of e to the square root t dt. And of course, I'll remind ourselves that the fundamental theorem of calculus is what we have right here, the derivative of these things. But notice the fundamental theorem of calculus only goes from a all the way up to x. Well, how can I deal with this? Because I've got an x cubed in my example, but I only have an x in the statement of my theorem. The trick is going to be chain rule. So what I am going to do is say that this thing here, this particular derivative, is derivative of some function g, the accumulation function we saw earlier, but that accumulation function composed with the function x cubed. So g of x is the accumulation function, and g of x cubed is that same accumulation function where every time there's an x, because of the composition, you put in an x cubed. Now why is that helpful? we know how to deal with g of x cubed. That's a simple chain rule. There's an outside function g, there's an inside function x cubed. We can do that via chain rule, so we say it's the derivative of the outside function at the inside function, the x cubed, times derivative of the inside function. And then final thing, how do I do g prime of x cubed? Well, the fundamental theorem of calculus tells us what to do with the g prime. So let's just do whatever the g prime is, and we're going to evaluate that at x cubed. We're going to compose that with x cubed. So g prime is just the same thing as f by the fundamental theorem of calculus. So in this we go just to f of x cubed, or in this case the x is e to the square root. So e to the square root of x cubed times 3x squared. So this was an example of how we could take something that sort of looked like the fundamental theorem of calculus applied to it, but not quite, and we managed to understand it as a composition and apply chain rule and apply the fundamental theorem of calculus and get that final value.